is by Mirte van der Eyden, and she will tell us about abstract cone systems. Yes, thank you.
All right. Yeah, thanks a lot. Thanks for inviting me to be here. And I will tell you about some work that's still ongoing. Hopefully soon there will be something on the archive about it. That's the plan this summer. It's together with Tim Netzer and Gemma de las Coves, both also in Innsbruck, just like me. And I will tell you about abstract cone systems and what that is, what I mean by that. But first, let me sort of start by some sort of teaser open problem, which is about tensor products of cones. So this will be actually a motivation throughout the talk for setting up these abstract cone systems. So let's think about convex cones. So they are like convex closed cones in some finite dimensional vector space, C living in vector space V and D living in W. And we want to take a tensor product of these cones. So this will be something living in V tensor W, this vector space. But what is it? What can we do? Well, there are a lot of choices, and maybe the first choice you think of is what we call the minimal tensor product, which is just the convex whole of elements from both cones separately, the tensor product of them. So we take something out of the orange cone, of the blue cone, tensor them, and take all these elements, take the closed convex whole of that, and this is a tensor product of cones. Well, there's actually another option you can do by taking somehow the dual of this. It's what we call the maximal tensor product, because it's bigger, what you get. The minimal thing will be inside of this. Don't worry about how it's defined. It's a dual notion, and it's another tensor product. And, yeah. Sorry. Somehow this doesn't work so well with my hair. I hope I'm still hearable. Okay, great. Okay, so these are two different tensor products you can choose, and there are many, many options in between. If we look at, for example, the PSD cone, so a specific cone inside the space of Hermitian matrices, so we have two cones of positive semi-definite matrices, we take the tensor product, there's a similar story. And the minimal option we actually call the separable tensor product, and the maximal is what we call block positive. I don't know if you've heard about this, but it's exactly what I told you on the last slide. But here there's a third option. So what you could also do, and what's a valid tensor product, is just taking the PSD cone in the bigger tensor product vector space. Yeah, so the D times E sized PSD matrices. This is an option, but for these general cones that I was talking about here, there's not really such a notion known, like a self-dual tensor product that's really sitting in the middle. Right, so this one, the max was dual to the min, but there's nothing really known in between, and I would really like to know it. And one reason that I would like to know it is comes actually from physics. So my main motivations come from quantum theory and also something called general probabilistic theories. So I know most of you are not physicists, but if you do quantum theory, then you talk about quantum states. And what are those things? Well, they're just elements from the PSD cone, specific elements. And what you do is you describe all physics using this cone, basically. But what people are also interested in is describing more general physical theories, basically to find out why is quantum theory just using this PSD cone, why is it so important, what are the properties, and so on. So they're also interested now in looking at general cones and thinking about particles living in there. But then if we have multiple particles or states, we need to take tensor products of these cones. And for general cones, it's not so clear, right? As I said, there's not really... Yeah, there's multiple options, and there's no self-dual one known. So, yeah, this is a question I'd like to answer. And there are many more open problems and questions in actually quantum information theory. I wrote some names down here. These words will probably not say much to you. But there are many open problems in this field that have to do with taking tensor products of cones, and particularly taking n-fold tensor products of things from cones for all n. Right, so we're not just having two cones, but we're maybe having n cones, and we want to tensor them, and we want to take this limit for all n and answer some questions about these things. And without going into detail, this will be my motivation of looking at these tensor products of cones. Okay? And the tool I'm going to use for this is something called abstract operator systems. So this is known. I'm going to tell you what an abstract operator system is. It will be about cones living in a vector space V tensor matrices, square matrices of some sizes. I will come back to this, but this is, you can see it as a tool. It's like a theory. There are things known there. There are theorems, proofs, etc. And there are connections to quantum info. But there are not, like, always there are these matrices there and so on. So these problems that I talked about before, we cannot really answer them with this tool. So what I want to do is generalize this. So from abstract operator systems, I will go to abstract cone systems, where we can do the same thing, no longer for matrices and so on, but for general cones, and hopefully use that to gain some insights in these questions that I talked about before. Yeah, so in this talk, I will first tell you about abstract operator systems, because probably most of you don't know what this is, and then I will generalize these and tell you a bit what we have been doing. Okay. Yes, okay, let's go. So what is an abstract operator system? So we will start with a real vector space V, finite dimensional. And what we do, what is an abstract operator system, or AOS? It's a family of proper cones. So what are proper cones? They are exactly what I talked about before. They are convex, they are closed, they are non-empty, and they are salient, meaning that they're really pointed. They don't contain any full subspaces. We have a family of these cones. Inside V tensor the Hermitian matrices of size S for every S, right? For SS1, SS2, SS, etc. All of these cones, well, a family of them, and not just a family, of course, but they have to be connected in some way. And they are connected in the following way. If you have something in your cone at level S, so in ds, then for all matrices of size S times T, so rectangular matrices, the bracket should be closed, of course, you can sort of sandwich your element from the cone with these matrices, and the size will change from S to T, and you should end up in the cone at level T, right? So this is a way that all these different cones should be connected. And this is what we call an abstract operator system. So what we get is all these levels, right? We have different cones in different levels, and they are connected by these contractions where you can go from one cone to the other. So let's look at an example. What we can do, for example, is, so we can choose this vector space, right, this V. And what you could do is choose, again, also Hermitian matrices as that vector space in some fixed dimension. And then you should pick cones inside Hermitian matrices of D times S for every S. Okay? So what cones could we pick? What could you think of? Well, maybe one option is to choose the PSD cone inside all of these layers. And this is valid because with contractions, you will again be a PSD cone of a bigger size or smaller size. So this is something you could do. But what you could also do is, again, different options. What you could do is take the minimal tensor product of these two PSD cones. And this will also be a valid abstract operator system over this vector space. Or you might see it coming the maximal tensor product that I talked about before. Here's the definition, but it's exactly this dual notion. And this is exactly sort of things that are interested also in quantum information theory, because this PSD cone example that sort of describes all quantum states, all bipartite quantum states, like there are now two cones, two particles. These are exactly the separable states out of the minimal tensor product, and that other thing is what we call block positive matrices, and physicists are also interested in those. So in general, for any vector space now, not just in this example, we can pick a cone in our lowest level, so just in our vector space V, and there will always be a minimal and a maximal abstract operator system created over that cone, right? So if we just fix the lowest level, the rest is not fixed yet. There are different options we can choose for the other layers, but there's always a minimal option and a maximal option, exactly given by this minimal tensor product and the maximal tensor product of the cone we pick on the lowest layer and the PSD cone. So this PSD cone plays a very central role here, right? Like that's really the one it's really based on that. Yeah, and again, for the example we just had where V is the Hermitian matrices, the minimal option was these separable matrices and the maximal option were these block positive matrices. Okay, so I mean, I'm now just giving you some sort of results about this abstract operator system such that you can hopefully appreciate when we generalize it, that these things still hold, because that's, of course, the aim. So you can also compare different abstract operator systems on different vector spaces. There's a natural notion of morphisms between them, which are the completely positive maps. So if we have an operator system D over V and E over W, then a completely positive map maps V to W in such a way that all the cones in all the different levels are sort of preserved under that map. So if we just use an identity on sort of the matrix part of the tensor product, then we end up in the right cone. This notion will come back later, shortly. So let me just state one more sort of interesting theorem about these abstract operator systems, and this is the Choi-Efros theorem. And it says that that actually every such abstract operator system has a concrete realization. What does it mean? It means that there exists a linear map phi mapping our vector space V to the vector space of bounded operators on some Hilbert space. And that an element is exactly in our cone at level S if and only if this thing here, where we map V to the bounded operators on a Hilbert space, so this full element, like applying phi times identity, will make us end up here in this space. So we can have a notion of positivity there, namely positive semi-definiteness. So if and only if that element is positive semi-definite. Yes, so this all sort of lives in the C-star algebra world of bounded operators on a Hilbert space. And a particular interesting class of abstract operator systems are the finite dimensional realizable ones. And these are exactly the ones where this Hilbert space is finite dimensional, the one you can pick. So then basically this map just goes to some matrix space, right? So, oh, and these are also known as free spectrahedra, if this is something you've ever come across. But that's like just a different terminology. Okay. Sorry for this, it's really just not sticking. Okay. Anyway, yeah, so this idea of being R-dimensional realizable for some fixed R just means that there's really a map from V to our matrix space of dimension R, and that checking if basically this whole operator system is equivalent to just a system of PSD cones in these corresponding dimensions where this R sort of plays a central role. Yeah, so an element will be in that level S on the left, if it will be, that element will be in level R times S on the right. So this was just sort of a quick overview of abstract operator systems and things that are known about them. And maybe you saw that there are indeed that the PSD cone plays a central role, and that there are sort of many things known there. And there are even many more things known there that I will not go into. So there is a notion of finitely generated systems, where you just pick a few elements and generate the abstract operator system containing them. There's a notion of duality, and choice theorem and Arfvedson extension theorem, if you've heard of them, they also sort of live in this world of abstract operator systems. But what we want, of course, and there are some links to quantum info. What we want, or what I would like, is to use this theory that exists to say something about these things I'm interested in, which is general probabilistic theories, about these problems in quantum info that involve many tensor powers, or about finding the self-dual tensor product, which will also help in these other things. So what I want to do is I want to capture these with abstract operator systems, but of course I can't do it yet, because we have to go beyond these matrices and these PSD cones. We want to just go to any cones. So that's what I'm going to do, right? So I'm going to change this operator setting to any cones. So what do we need to change, really? Well, before our abstract operator system, all these cones lived in V tensor matrices of a certain size S. Now these have to become some other vector spaces that I just call S. And instead of contractions that I have to use to map in between these cones, I have to select some other type of maps, right, to connect these cones. So I have to come up with something. And the structure we came up with to sort of do this in a way, of course, that all these results I talked about, or at least listed, still hold, because that was what we wanted. What we did is we used some category theory to sort of do this, and you don't need to know any category theory to follow this talk, but just don't get scared of the word. So basically these are the things we needed to choose, right? These vector spaces and these maps that we select, and we call this an index structure, because before it was just these indices S. And this index structure is somehow given by a category. So a category is just a bunch of points and arrows, basically, in a nice way. And what we want is we come up with such a category, So think about this category basically as our level structure. So before we just had our levels S is 1, 2, 3, 4, etc., right? And we could move between levels by contraction, so these are the arrows. Yeah, so that was sort of what you can think about. And we want to map this level structure, this index structure, with a functor, which is the relevant morphism in this case, to the category of finite-dimensional vector spaces. So what is this? Just you have all finite-dimensional vector spaces, and all these arrows between them are linear maps, because these are the relevant maps between finite-dimensional vector spaces. So what such a functor does is it picks an element there in that category, maps it to a vector space. So in this way, we can pick vector spaces that we want. Okay? And it maps the arrows that we define there to which of these linear maps are we going to use to go from one level to the other. So before, and often this functor, by the way, it's not injective, it's not surjective, so we really just pick some in some nice way. And before, of course, the things we wanted to pick for abstract operator systems here is the vector spaces of matrices, square matrices of certain sizes. And we wanted to pick exactly those maps that were these contraction maps, which is a subset of all linear maps. But now we can do much more. And of course, we cannot just use, you might sort of already see that, we cannot just use any category and any functor. I mean, this is like super, super general, but they need to be nice in a way. And in the specific way that they need to be nice is called, the category is called star autonomous, and the functor is called strong monoidal star functor. Don't care, it doesn't matter exactly what it is, but I just want to give you a bit of a feeling of what that means by looking at an example. So one thing we could do is, on the left, as our category, we can now choose whatever we want. For example, we can again choose finite-dimensional vector spaces. And I will show you that this has some sort of nice structure, which is exactly what is called star autonomous. And the nice structure is that for any two vector spaces, there's a notion of a tensor product in this category, and the tensor product of two vector spaces is again a vector space. It's again one of these objects in the category. Yeah, that's sort of nice, and that's something we want for all of our examples. Moreover, the set of linear maps between two vector spaces is also a vector space. And this is also something we want. So all these arrows together are represented by another object in our category. Moreover, there's also a notion of duality. There's for every vector space a dual vector space, which is actually linked to also a set of arrows, namely it's of course just a dual vector space, all maps from our vector space to the base field. Okay? And actually you can also again express these linear maps in terms of the dual and the tensor product like this, as you might know, right? Like the maps between one vector space and another one are exactly represented by this. Objects from that tensor product vector space. So this is what this is an example of star autonomous. It's even a little bit stronger, actually. It's like a particularly nice example. But this is something that works. And if we just now choose as our functor the identity, because we map to FVec anyway, to the same category, then this is a valid underlying structure. So we could choose, this means that we could choose all vector spaces and use all linear maps to move in between them. And we can define an abstract cone system like that. Another example would be a category where we pick as objects cones inside vector spaces. Yeah, so all cones inside all vector spaces. So every vector space is in there a lot of times with all possible cones inside. Yeah, many, many, many objects. You can do this. This is a category. There should, of course, be some arrows as well. So what do we pick as our morphisms here? Well, we pick the positive maps. So all the linear maps that map one cone into another cone, inside another cone. This is a category, and this is also such a nice star autonomous category, because we again have a tensor product here, and we can actually, there's some choices you can make, but actually the minimal tensor product works very well in this case. So you can of course take the minimal tensor product of cones, and it's again one of these objects, right? Because we already picked all cones in there, so this is also one. Also, we can express these maps that we picked in terms of our cones again, like this, where we actually have to use the maximal tensor product, which is okay because in the star autonomous category you can have sort of two tensor products. So this works well. This, if people know the Choi-Jamiolkowski isomorphism, it's basically exactly that. Yeah. And again, we have a notion of duality because we can talk about dual cones, which are exactly the positive functionals on a cone. Yeah, so this gives us another example. And if we want to now use a functor, choose a functor, we can use the forgetful functor, which what it does is it just forgets about the existence of the cone. Yeah, it just maps this C, V to the vector space V, but it does remember the maps. I mean, something should be remembered, right? So the morphisms are remembered, and in that way, this whole cone structure still is remembered. So we have some other examples, actually even more than I listed here. The first two I talked about. The third one is we can, for example, choose all simplex cones. It's what we call S-cone. It would also work. And if we choose, I'm now not going into detail, but this fourth option will exactly give us back the example of abstract operator systems. Because we basically we choose all Hilbert spaces, and we map them to the bounded operators on Hilbert spaces. And in finite dimensions, these are, of course, basically the matrix spaces that we would use in our basic example of abstract operator spaces. And now, because I still have maybe 2 minutes if I want, I just want to tell you that we can again now define, of course, what we call an abstract cone system in exactly the same way. So it's a family of cones living inside these vector spaces in the image of our functor. Yes, and they must be connected by all morphisms in the image of our functor. As I explained already in the picture, which is maybe even more clear than seeing this now in a formula, but that's exactly what it is. That's how we define it. And I mean, you can actually define it even a bit more cleaner in terms of functors, but I'm not doing that here. And the point is that we can do all of this again. Yeah, so there's a minimal one, a maximal one. We can talk about finite dimensional realizations, blah, blah, blah. We can do all this. We constructed it, of course, in a way such that this all still works. And we also see that there actually are some other examples than just the one we started with. So that's nice, that's fun. And actually the nice things that we got out of this is that actually by reproving all of these things in this more general settings, we found some much easier and sort of more intuitive proofs also for the things that were already existed in the case of abstract operator systems. So that's something nice. And we found some sort of nice surprising connections. So for example, there's this Arfveson extension theorem that I said. I mean, even if you don't really know what the theorem says, it's something in the world of abstract operator systems. But by choosing different index structures, we can sort of now see what the theorem says in that setting, right? So by choosing FVec or Fcone or Scone, and it gives us all these other theorems that are also already known and have like names, such as like it gives us for vector spaces the homomorphism theory of vector spaces. For cones, it gives this thing called the Riet's extension theorem, and for simplex cones, it exactly gives you Farca's lemma. So all these things are sort of connected in this more general extension theorem in our setting. Finally, this is really the final thing I want to say is another fun thing we sort of found out is that this actually gives us sort of a hierarchy of examples, because if we would now look, and now it becomes maybe a bit crazy, at the category of all abstract cone systems, so points here are now abstract cone systems, maps are completely positive maps, then this category is star autonomous, which is the thing we used. So by using this category of abstract cone systems, where we have fixed sort of our underlying index structure, choosing some functor in the right way, we can sort of start building on that, right? So by having examples, we create a hierarchy of more and more examples. So it's great fun. So just to summarize, I told you about abstract operator systems a little bit, some sort of results that are known, some connections, or at least hints at connections to quantum theory. And I told you how we have been generalizing this to something we call abstract cone systems, where all these theorems still hold, where we have more examples than just that case. But of course now what we've been started doing, but what I haven't talked about this at all now, is how this helps us, right, in all these motivations that I had in the beginning. So how can we use this to say something about these tensor products of cones? What are now the applications to GPTs, quantum theory, and so on? But this is all going to happen in the future, I hope. Thank you.
Okay, is there any question? Yes.
So this functor, you mean? Yeah, so basically this functor has to... sorry. So he asked me what this strong monoidal star functor means. And this basically says that, it needs to preserve some sort... We wanted this category to be nice star autonomous, right? And this functor has to preserve some of that structure, otherwise it wouldn't be useful. So it has to preserve, for example, the tensor product. So if you have a tensor product and you apply the functor on both things separately, it should be the same as applying the functor on the tensor product object. And it should also preserve the dual. So that's basically what it means. It needs to preserve the tensor product and the dual.
If there is no other question, we thank Mirte again.